Hello. For those of who for those of you who do not know me, I'm Brandon, and I'm here to present to you about co-packaged optics. So the first thing I'm gonna mention is kind of why I decided to research this topic. Well, the reason I decided to research this topic is I'm a little bit interested in quantum mechanics, and photonics does rely a little bit on quantum mechanics. There's a lot of research and industry going on right now, um, with like AI and data centers and everything like that. Optics is really important because it does allow for faster data transfer and lower power, which I'll talk about in a second. And the other thing is, I interned with Marvell, which they do a lot of uh, optics and do a lot with this. My team didn't specifically do that, but it was in the company and it interested me. Which leads me to the last thing is I just kind of wanted to learn more about it, and I thought this would have been a great opportunity to kind of learn about co-packaged photonics and what it is and what's going on. So, moving on, what is photonics? Photonics is basically just like transferring data around with light. An example of this is like internet. A way that we get transmit internet to different places is we use fiber optic cables, and this allows for like gigabit speeds. Um, as you can see, this image right here is some fiber optic cables, and you can see you can see transmit light through it. Um, One way we do this is we use lasers, and lasers are nice because you can make those with Gaussian arsenide, as Gaussian arsenide is a direct band gap. And again, like I was saying, using fiber optics allows for really, really fast connections. So data centers, and by extension AI, really likes fiber optics or photonics because it allows data really, really fast data movement, and it can allow for really, really high speeds with a bunch of channels of fiber optics, like in the terabits per second. So moving on, I just decided to go over a couple common terms in case I forget to just say them. The first one is EO, or optical engine. Um, it's basic to my understanding. It's the thing that converts uh, op, optic uh, optical interconnect into an electrical inter, into an electrical signal, so it can work with other parts of the chip. PIC, or photonic integrated circuit. It's a photonic. It's a light integrated circuit. It uses lights instead of electricity. EIC, kind of like the normal IC we're normally used to. EIC, just to specify, as we have two different types of ICs. And then waveguide. Waveguide is what the light would follow, like the wire. It'd be like the fiber cable, as an example. So yeah, those just some of the common terms, or things that kind of in case I forget to say them. Uh, just want to Next is why this subject is important. Like I was saying, uh, it allows for faster data transfer. And I was saying with AI, um, that requires it. AI does need that faster data transfer, especially data centers that need have really fast connections. The other thing is it does use less power moving data this way. Fibers has less loss than electricity or copper. So if you can transmit things over fiber, it does save energy. And as AI does use a lot of data, like this graph I have here, this is a study done by Berkeley, but they predict by 2028 that the total U.S. energy usage, uh, with the total U.S. energy usage, 6.7 to 12% of that could be for data centers used for running AI, which is a lot. Like by 2028, they're thinking 1/10 of the U.S. energy goes towards data centers or AI, which is a lot of power. So any way you can reduce the amount of power and increase the speed, these companies care a lot about. Um, Moving on, some of the going into a little bit what the history of co-packaged photonics and some of the limitations. At first, it was just pluggable photonics, so you'd have a device you'd plug into something else to allow optical interconnects. Then it moved to on-board, so then you could plug the photonics into like the PCB or the optical interconnect to a PCB, and then it could connect to like your normal EIC. Then we got to co-packaging, which you have it on the same substrate, so it'd be on the same chip. And now there's like, uh, opt. Then the step above that is using like an interposer and connecting it on the same substrate when you start getting more and more packaging. Some limitations with it is like the vendor, as there's different vendors like Broadcom, Marvell, Lightmatter, all different companies. They you can get locked into like their system. Another issue or another like limitation is the signal/power with them, or that's like a consideration at least with designing. Also the scalability. So those are like the considerations when designing or using optics. Moving on, some of the current market or what's going on in the current market. Marvell and Broadcom, when I was looking at some of their articles, they're claiming to have about 200 gigs per lane. I Another company that is doing some interesting things, and I'll talk about later, is Lightmatter. They're making photonic interconnects in their package. And then another company I read about doing some stuff, NLM Photonics and iMac, also along with Marvell and Broadcom, are working towards the 400 gig per lane. And NLM Photonics and iMac are two startups. And those two images are just two different like optical interconnects, one by Marvell and one by Broadcom. Moving on, talking about the package itself. Going into like the different types of packaging, 2D packaging is all the chips are the same type on the same interposer. 2.5D packaging is you have like a discrete chip like the DSP in this example with like the silicon photonics interposer with the chips attached to that. Then 3D packaging is packaging with your silicon photonics with your DSP or your discrete EIC with your photonics chips all attached on like a stack. Some of the considerations when packaging is warpage, underfill. Underfill is interesting because the edges of the package have to be kept clean for the photonics interconnect. So you have to be really, really precise with how you do your underfill. Another thing I found is attaching the ribbons and like attaching the fibers and protecting them. And some considerations making sure those connections are secure. And another thing with like TSVs, silicon photonics is thicker than normal silicon, so silicon vias have to be bigger. Moving on, some of the innovations I saw in fiber connections is vertical connections. So instead of like having like the fibers connect horizontally, you can do something kind of like what this graph does right here, and basically have a 90 degree or 45 to 90 degree angle of the fiber coming in and attaching into the integrated circuit. The advantage of this is you can put fibers coming from the top, not just the side, and it has pretty low loss on the interconnection. Another paper I found a way to create like a connector that uses like a core to align the waveguides. And another startup, Advensa. I'm bad at pronouncing that name. This name right here. They're using micro LEDs. So like instead of using like a laser to send data through a fiber optic, they're using micro LEDs or just like a blue LED to transmit data. You can't put as much data in like a LED like that as like with a laser. You can have multiple channels of light, but it is simpler. Moving on, I talked a little bit about silicon photonics and using that as an interposer. So I'll talk about like what it really is. Silicon photonics, like just normal silicon or like making like a an IC or an integrated circuit, you can do that by making like waveguides and running like light through it instead. Like this image right here is like of a example of like a silicon photonics chip. So instead of like running like electrical wires through a die or like copper or whatever, you can actually use that same technology to make like photonic interconnects and like waveguides and stuff like that inside a chip. Some of the technologies I found around this is trying to embed like a silicon photonics chip into the substrate, like an organic substrate, stuff like that. Trying to do like 3D stacking, like placing the EOs on top of the chip, networking, then like having like a silicon photonics like interposer to connect like all the like EOs and like the EICs on top of the chip to like each other using photonics, which is something like Light Matter does with some of their technology. So, yeah, some of the things going on with that. Then going into, there's a lot of like talk about that I noticed about like changing the interposer. One of the big ones is like changing it to glass. Glass has better electrical and photooptic properties than silicon, which allows for better loss. But it seems like it's a different process to use glass than like silicon photonics. One of the other things one of the papers I read claimed is it's easier to embed chips or like embed like the ICs into the substrate in glass. So there's stuff like that. As you can see, like this picture right here, this will allow for a bit easier like 3D packaging, as you don't need to be running TSVs, as you can be using like through glass silica vias. And to my understanding, the advantage of doing that is they can be smaller than silicon. So yeah. The downside to my understanding of this, as it sounds like it's very different than like silicon photonics, is it may require a different process than using like the already existing technologies that we have for normal IC development. Moving on, another technology I found that was really interesting is EMIB, or Embedded Multi-Die Interconnect Bridge. This is developed by Intel, and what it is on the second layer of the substrate, they're using like making really small bridges to two dies, which I think is a really interesting idea in the sense it removes the need for like an interposer or like a redistribution layer or something. Well, expanding that, they're trying to use that for optics. So like they're using that for just normal, just normal co-packaging, but they want to use it for optics. So what they've been doing is attaching like the optical I/O that would like take the fiber in, and then attaching that to like the EIC using their technology. And I have that image right here, or it'd be like on this side. Yeah, right here. That kind of like shows that. Another thing they also are trying to do is like embedding like an FPGA with it. So they have like some optical interconnects, like 5 or so, that go into like an FPGA using the EMIB. And the last thing, just to like try to reduce the size and like reduce the need for like 3D packaging, is try to make a cavity and put the PIC, or like the optical I/O, into the substrate, and then use the EMIB to embed it, just to like further shrink the chip. So yeah, very interesting technology to try to reduce the need for an interposer. The last thing I'm going to talk about is Light Matter. So Light Matter is a startup company, I'm pretty sure based out of Mountain Home, and they've developed a lot of really, really interesting optical technology. One of the things they claim they can do is transmit at around 400 gigs per line, and how they claim they can do this is by having this one fiber transmit and receive at the same time. So they can send data and receive data on the same fiber line on the same time, at the same time, which I think is really interesting. The other thing they have is on their Passage M1000 chip, their interposer is a reconfigurable waveguide which routes throughout their chip, which on top of their interposer is a whole bunch of GPUs or their chips that all have like that networking, uh, like the like that 3D networking thing I was talking about earlier. They have all their GPUs on top, and then those GPUs or those like EICs connect into the chip through the silicon photonics interposer and use photonics to connect and network with each other inside the chip, which is really interesting to me. It's like I just find I think that technology is really interesting. So it's a 3D packaging with the substrate, then their interposer that networks all the chips to get all their like EICs together, and then at the top is like their EICs and like the conversions between photonics and like electrical. Anyways, just to summarize a little bit of what everything I've talked about, um, what the first thing is a vertical interconnects to allow for more interconnects on a PIC or a photonics integrated circuit. The silicon interposers and kind of some of the technologies around that, swapping to a glass interposer, Intel's EMIB technology, and just some of the things that light matter is doing. Anyways, I guess I'll give my closing thoughts a bit. Um, I thought this was really interesting to research. There's a lot of interesting technology going on around this right now. And I think there's a lot of cool things that can be done with light, like co-packaged photonics and like networking through light is one thing. Another technology that I think is really interesting with this is you can go like light computing stuff. Oh, I think there's a lot of technology in photonics, and I think it's just an interesting subject. Anyways, any questions? If not, well, thank you.